we've been working on the premise of making the world's least expensive launch vehicle. And our work started in an austere setting. And that is what has driven all the development we have in terms of making a rocket that we could afford to build. This whole process was initialized by seeing an article on Lutz Kaiser from Otrog in the 70s. He started the world's first commercial rocket company. We read with great interest how he was using off-the-shelf products to make his launch vehicles, to do a modular approach that was something that would make manufacturing easier and cheaper, to really just bring the price down of doing rocket launch. And that became our goal, to do something that would take things, and this was very early on. This was when it was only governments doing the types of projects, space projects, rocket projects. And so he was a real pioneer in that. And he eventually went on to work with him, but he was unconsciously a mentor to us for just by his very existence and doing these things.
Did you meet him?
Yes, he came to work with us. It was probably for 3 or 4 years we collaborated on a number of projects. He had seen the fact that we were using different propellants, which are nitric acid and turpentine, those are storable propellants. Everyone else is using cryogenics, liquid oxygen, and kerosene generally for RP1. But we like this concept of not having to babysit the propellants, not having to have it hooked up to the last minute to top off the rocket before launch, but have the luxury of being able to fill a rocket with a combination of propellants that allowed it to sit for an indefinite time before you launched. So this was a safety factor. This also gave you an edge in terms of your logistics. You could sit for days or months, or in some cases years, and be at the ready, as it were. And in our case, we took it upon ourselves to eliminate any failure-prone or vastly expensive systems that were cost drivers, also in the whole pricing of rockets, and to really take the rocket down to its essentials, to what the essence of what a rocket is. And in this case, we eliminated turbopumps, which surprises a lot of people. But we have a pressure-fed vehicle. And this radical simplification also is not easy to achieve. It's an incredibly difficult 3-dimensional chess game. You change one component and 2 or 3 others change because of that. But in order to make a rocket that would, as the people who started this whole movement in the 70s, 80s, and 90s that had intended to radically bring down the cost, you had to do something different. And you hear the Jobs quote, "Think different." This is different. This is a different rocket. We're a lot of times we're demonized because of the types of propellants we use. We have a history of let's say having difficulties even in competing in maybe the Lunar Lander Challenge. It was interesting. We signed up for that as competitors. It was the Lunar Lander Cup, I believe it was. It was a NASA centennial program. So the day after we signed up to be contestants in that, they changed the rules and outlawed our propellants. So I thought, oh, this is amazing. What's going on here? And our propellants aren't hypergolic in and of themselves. They outlawed, but they thought they were. They outlawed hypergolics, listing hours, and even though ours is hypergolic due to a chemical fuse, but we were, as I said, we've had a very hard time pushing this rocket concept because of the peer pressure of everybody, again, building that same Delta 2 or whatever it is that they're copying. With Musk's success, and it was great what he did, getting that whole thing going. Everybody else decided it was the only rocket you could build was a LOX kerosene rocket, and would constantly receive pushback. We did at one point get backing from NASA with an SBIR in 2012 for the development of our Neptune launcher, and that was a surprise to us and thrilling. But we've run this on a pretty much a shoestring budget. But what we've done so far is we have flight tested, and you'll see the photos of the engines here. That's our test site in Mojave at the Mojave Air and Spaceport, where we've been established since 1996. But we make all our own engines. Those are ablative engines. That's a very simplified type of engine, types used in the original moon missions. We do a variety of, again, simplifications of ConOps. We have a philosophy that is pretty much taken from the minimum cost design philosophy that came out of a study done at Aerospace, I believe, in the 1960s, which showed what would be required to reduce the cost of space launch in the US, basically. Or it was a very, very penetrating document in its focus on what was being done in terms of waste, what the actual type of rocket that could be made and could be affordable would be. So we followed all that advice, and we came up with the rocket system that we have now. That we're actually looking at being able to do orbital launches from mobile locations, both sea and land, to LEO for under $1 million. And that's been our goal the whole time. And it's costing out to look like that's going to be the case. We're looking at doing the first orbital launch within between 12 and 18 months based on funding. And we have been raising our own funding initially over these years through the sale of our satellites from our satellite division. We have satellite kits. We do that. But that's been the kind of the bread and butter of the company for all those years. And when I say all those years, that's what, 27 years roughly. That's the problem. If you raise your own money, it just takes longer. But we've seen a lot of companies come and go who were like geniuses at getting funding or doing a venture deal or things of that nature. But then they're basically amateur rocketeers with a giant war chest of funding. We've gone through all the steps. We have a moon mission come up in the slides there called the Lunar Station that we're planning, that will be a precursor to what we hope is our first commercial base on the moon, which would be served by this transportation system that we're now creating the rockets to operate in that system. So the Neptune rockets, the Scepter follow-on, the Scepter freighter, we're looking at cargo, basically space truckers, I guess, in this case. But it's a labor of love, let's put it that way. It's something that everyone involved in this program lives and breathes nothing but rockets. And the fact that we have an internal revenue stream that allows us to do this has worked for us. We have 190 plus payload customers for our satellite kits in various countries around the world. About 25 countries use the kits as STEM, the center of STEM curricula in their academic programs. And so that's basically it. It's a bootstrapped company that is producing the world's lowest cost rocket, about to go operational next year. So that's where we are. So Priyan, any questions on that, or anybody out there?
Yeah. Let me ask some starting questions, if you don't
Yeah.
mind.
No.
So these are kind of softball because I've known you guys. So everybody says they're building a modular rocket, and you said, but in your case, it actually means something different. Can you talk about?
There's a module. These are, yes, each one of these is considered a module. These units.
No, why don't you explain the concept of horizontal stick?
Okay, and we have a concept tank bundling. We can nest the stages so that we have stage one would be on the exterior. Say these would be individual individual rockets. Let's say a rocket unit with either 4 cylinders that are the propellant tanks and an engine, or a single tank and an engine. That's considered to us a common propulsion module, a single module. So we bundle these modules depending on a mission requirement. And in this case, the engines firing here are 7,500-pound thrust engines that are the basic propulsion system for anything. But it's a cumulative thrust if we bundle a number of these modules together. So in the current case of the Scepter that we're working on now, Scepter freighter, we have a outer ring or outer layer of stage 1, and inside that is stage 2 and stage 3. It's like Russian nesting dolls. Gives us a very wide top to the rocket for large payloads. And the ease of build in that is that they're identical rocket engines, they're identical tanks. Everything is the same. So this is very, very easy to automate in terms of fast build and rapid response. So our goal here is to stock our own shelves with our own components, our own rocket kits, as it were, to put our rockets together in bespoke fashion to mission requirement order, and do that quickly.
Okay.
And when we say quick, it is
There's a picture in your slide rotation here that shows a carbon fiber. That picture right
Yeah.
now shows this.
right.
So correct me if I'm wrong. You do your own carbon fiber wrapping of your own tanks.
Yes, if we use tanks that require fiber wrap, we do that. We operate again on a very low budget, a budget that would frighten most rocket people. So we couldn't afford to buy a filament winder, so we built one. And that's generally the philosophy at Interorbital, is if you can't afford it, you build it.
But you have a history selling carbon fiber reinforced tanks. Do you not?
No, we actually do not at this point. We've had inquiries along that line, but we actually have made tankage for other aerospace projects like the Dick Rutan's Around the World balloon venture that he did in 1997. That was our first aerospace contract, and we made all the propane tankage for his balloon venture, and then fitted those out with systems like directly taken from our rocket work to be able to allow them to control the propane flow at altitude. So so that we have done that. But
More question.
these we do not send out. Yeah. Mhm.
One more question. You mentioned your nitric acid turpentine propellant and the
Yeah.
sort of bad reaction this gets.
Yeah.
So why don't you
Mhm.
explain why these other people, why they're wrong, and why your propellants, not just because
Okay.
of their storability and their
Well,
room.
Yeah, these are very, very high density propellants. They're like, you compare like water to a thick corn syrup or something. Obviously, the very thick liquid is higher density. So these liquids, or these are liquid propellants, have very heavy. They have a lot of power that fits in the same space as actually a very small, a much smaller space than, say, a cryogenic liquid, which requires huge. You've seen you remember the huge tank on the shuttle. That was required because those were cryogenic.
Low density propellants. Like
Exactly. And in our case, that allows us to build a smaller rocket because we don't have to have that gigantic storage area, which is more economical to do that. And turpentine is these are these are the ultimate green propellants. Turpentine is made of pine trees, right? And
and nitric acid, as I recall, if you spill the nitric acid on the ground, you hose it down with water and it's basically fertilizer.
yeah, it is fertilizer, and it's used as or fertilizer industry is probably the largest consumer of nitric acid out here. And yeah, these and they're safe as well. In fact, the Navy was, before the advent of solid rockets in use by the Navy, they were looking at bipropellant liquids, and nitric acid was chosen as to be used because of its safety factor, and that characteristic that they liked was that if there was a spill and propellants came together, and they in terms of the ones they were using, they would go up in a fireball rather than propagate a detonation like liquid oxygen and kerosene. But our particular ones don't ignite on contact. They need a fuse in terms of chemical liquid. Yeah, then it's not like nitrogen tetroxide and UDMH. It's which ignite on contact. These can be made to ignite on contact. Like SpaceX uses the TTEB.
Hey, sorry to interrupt. If Rod is going to talk, he should get closer to the mic because he's just,
Yeah. He just chimed in there for a minute. Yeah. Okay. And then, so these are characteristics of the propellants that we like, plus the fact that it allows us to have rockets ready for rapid response work should they be needed.
Right,
Now,
okay,
that
so
could be-
let's summarize here. The propellants are
Mhm.
non-cryogenic and hence storable for long periods
They're
without.
non-cryogenic,
They're
storable.
they're non-hypergolic, so they don't ignite even if they mix without
Yeah.
external ignition. They are green in the
Well-
sense that if they spill, they're not going to kill anything. They're non-toxic. And
Well, they're corrosive, but they with proper handling, you can. This is something and something you should do with every propellant. There is no safe propellant combination.
and they are dense, so you can pack a lot of energy into
Yes.
it.
And you get an additional boost from the density specific impulse of those propellants. So these are all pluses. There's so many pluses to it that the so-called negatives or which can be easily mitigated with proper handling, proper clothing, those sorts of things. These are it's our choice, and it was a choice of Werner von Braun for his Mars missions.
Oh, really?
People
So
who make
also, isn't
Yeah.
another advantage of these propellants, and correct me if I'm wrong, is that they're industrial chemicals that are in wide use.
standard industrial chemicals can be transported on the highway without military escort. Yeah, and cheap in terms of I don't know if you priced UDMH lately, but or anything like that. But these are pennies on the dollar compared to those things that cost hundreds and hundreds of dollars a pound. And when you're talking about a rocket, many pounds involved. Many tons of propellant, in fact. So, and when we're looking at the bottom line for our customers to be able to do space launch and have orbital access for a reasonable cost. Like I said, Musk did a good job in bringing it down from the really astronomical figures that it was before his work. That's still an exquisite rocket system. This is a harkening back to the concept of the big dumb booster. I don't know if you remember that, which was very popular when say Beale and a lot of the people were doing the initial rocket work in the 90s. Everybody was after the cheapest, most brute force method to get to space as possible. And that kind of went away when Musk had his success with the cryogenic rocket. But we've persisted in this quest for the lowest cost vehicle and one that is smaller profile and easier to handle in terms of just general logistics.
Okay, Allison, do we want to move on to chat questions and audience questions now?
Yeah, that'd be wonderful. Micah, do you want to go first?
Sure. You indicated that you were shooting for less than $1 million to get into the lower Earth orbit. What do you think, assuming you had optimal payload size for whatever that is, what do you think the cost per kilogram for a payload would be?
In terms of these initial rockets, we're looking at about somewhere under 5,000. This is as the rockets progress through the various iterations, which go from initially the Neptune and the Scepter freighter and the Triton vehicles that are very large vehicles. We're looking at getting it as low as 2,000.
Okay, that's good. And Jared has a bunch of questions. What is the exhaust gas composition of the rocket?
It's actually interesting you ask that because those are cleaner than liquid oxygen and kerosene, and largely nitrogen, some water, some nothing to the point of considering it a hugely dangerous exhaust. In fact, it's considered a green type of exhaust.
Does your rocket, I'm just ad-libbing from these audience questions. Jared, do you want to,
Mhm.
or should I ad-lib them for you? All right, I'm going to do it.
I'll unmute. Do you
Okay.
see me?
Yeah, we can hear you.
Okay. Hats off to you for what you're doing. I'm a mini version of you. I only have 3 years in, but I believe the same as you. A lot of the things that you're doing with big dumb boosters and simpler is better and cheaper is better. My chief engineer worked for Robert Truax. He was
Oh, okay.
his name is Craig
Right.
Adams. You may have heard of him. A lot of the
No, but I
things-
knew Bob.
Yeah,
Or I knew Bob.
but a lot of the things you're talking about, they're into. I'm even more radical than you, and also understanding the headwinds that you are running into. But hats off.
But-
I just wanted to say hats off to you, and I was curious what the exhaust was.
Yeah, it's quite clear. And when you say more radical than us, what is it that you're doing that puts you in that category?
My fuel source is water and heat, and I believe in using heat as a fuel source and kinetic energy, and by eliminating a stage one by using linear acceleration, ground-based horizontal launch, using a steam rocket with supercritical steam, which has a great specific impulse, even safer than anything else. And inputs are only electricity and water, outputs are steam. It's just the launch facility is a bear at 40 kilometers long.
Yeah, so
Yeah.
you'll be interested in hearing Mike Grace speak at an upcoming workshop.
I've spoken with Mike. I know Mike. We've had private discussions. He's got a lot of interesting things. Maybe we could even use some of his technology. But what we're doing is we're transforming the heat of the hypersonic shockwave compression and using the zeroth law of thermodynamics to not melt long enough to get to the thick stuff, and then to use that excess energy by applying it to the exhaust steam. So we are eliminating the heat from our system by pushing it out as exhaust, which is like the fundamental thing, what we call thermal scavenging. And so all
Well,
the-
that's actually cool that you're exploring other propulsion systems, and I applaud anyone who is, because I love that. I also love nuclear propulsion for rockets, and look forward to working in that area, because
I'm afraid
that's
of the radioisotopes
key
personally.
going to be the key to shortening trips to all the wonderful places in our solar system that we should be visiting.
Oh, we have another question. Nuclear
Mm-hmm.
propulsion is a whole other meeting. We have another question from Ian, and I'm gonna amend the question. So Ian asks, "What's the specific impulse of the current system?" And I think that's a great question, but I also want to say, along with specific impulse, you guys also focus on density impulse. So can you talk about
You know,
grades there and the sort of different ways to analyze
yeah,
performance?
it's 250 ISP that we're working with right now, and I think that's vacuum 300, something like that. Yeah, and so it's an additional boost, and we haven't yet characterized what that boost is, but it's evident from the work we're doing. So this is our ongoing testing will reveal some of that that's happening. But we know that having that, and the obvious deal that you have happening there is that your rocket mass is going to be smaller. You're for the same amount of power, as you say. There are a number of benefits that are inherent in that. But at this point, I don't have any figures on the density specific impulse. It's just a known characteristic.
What is your pressurant?
We would love to use helium, right? and so we're using, but it's an unobtainium lately. Hydrogen, in some cases, we use.
Interesting. And does each module have its own pressure tanks and its own, I guess it must. Is that the case?
It's blowdown. So there's no separate pressurant system as
see.
such. And and this really took a long time to perfect, I'll tell you. So it is not trivial. And again, it's something that was sought after again from the inception of the big dumb booster concept. This is something people have worked towards, and not many have achieved. Work is ongoing, but it is on our end achieved. So we're happy with what we have at this point.
Do you want to say anything more about your satellite kits? And
Yeah,
I know-
we in 2009 we introduced our TubeSat kit, which is another form factor in the small satellite family. So we're looking for a cheaper alternative, always looking for value for our customers, right? A cheaper alternative to the popular and more easily acquired CubeSats. So we did a project in-house and developed a more circular type of cylindrical form factor for the TubeSats. They slightly less mass and less expensive than the CubeSats. So we sold those to largely academic groups. So they were originally made as an exercise, say, for an engineering graduate school class. But it turned out that so many people were interested in it, and it's all the way from middle schools through giant corporations and government agencies that we developed a 2-tier pricing schedule for that, so that academics paid 50% of what the commercial companies paid. So our CubeSat, and then we packaged it with a launch as well. So it's basically a launch future. It was the CubeSats are 22,000 for academic. That's with launch. 44,000 for commercial or non-academic with launch. And as I said, we have at this point, I think it's 196 distinct satellite units that are waiting for launch. And our launch manifest is on our website at interorbital.com. So you can see there's a massive list of everything from space testing to advertising projects to
if your
art.
first launch fails, do you give them all an additional TubeSat kit and an additional launch?
No, that's not the case. But
Okay.
they're taking a risk, and they're getting this radically reduced price for as early adopters, people willing to take a risk.
How many TubeSats can you launch on one of your starter rockets?
We're looking at somewhere between 30 and 40 on the first phase, going up to about 150.
Okay, we have another question
Mhm.
from Ian. What are the storage requirements for the propellant? Is it well suited for long-term storage in space? And are there any challenges with relight?
Yes, it's storable. Yep, there are things that need to be done with anything that you're storing in space, but in terms of, it's not going to dissipate like liquid oxygen would. You're not like a cryogenic depot has many problems that a storable propellant depot would not have.
Yeah, a lot of people don't know this, but I understand it. Essentially, all rockets that use liquid oxygen and potentially other cryogenics, they have to, if they're going to do a burn to exit LEO and go to geosynchronous or lunar or anything like that, they have to do that burn within like minutes of getting into LEO, because if they come around into the sun, all the propellant boils off. And
Yeah,
so
so a lot of inherent dangers in using cryogenics that we didn't want to deal with. That was another reason we chose storables. It's more manageable.
yeah, but another thing about it is that you can launch to Earth orbit. You like have time to check things out and make sure stuff is working before you commit to a further orbit.
Completely correct. Completely correct. And that's the other thing. Also, if you're on a launch pad, when your weather comes up or somebody's in the launch zone and you can't launch that day, you don't have to defuel. You don't have to you don't have to top it off. All those things that are required that you see happening when we see conventional, and I call them conventional rockets because they are. The vast majority of the current rockets are are cryogenic. We have, I think we were laughing that our rocket is like the third world rocket. It's like where we've got the North Koreans and Iranians. I think.
And interorbital. I think.
Yeah, it's orbital. But there's a reason that people use these, and also maybe in a developing country, there's a reason for that. It's a cost factor, and for us, it had to be because we were again paying the bills ourselves. And so this is, but it's now it's reached the point where the technology has matured we actually even reached out a bit. We were doing a small raise. We were trying to get to build a factory in
So,
Mojave.
Allison, do you want to ask any questions?
Yes, I always have my kind of like what's the question kind of on the go. And so there's a few things that always interest people across our individual product areas. One of them is, for example, like a carrot of if you were successful, let's say in 5 to 10 years, where would you be? Like, what's a really good outcome that your technology enables?
I'd be having a cappuccino at my moon base, looking down at the Earth.
Uh-huh.
And in terms of the technology, like what would be possible if you were just trying to kind of paint a picture of
Well,
everything?
We're
kind of
looking
stuff
at,
the
we're
long-
looking at regularly scheduled flights between Earth and Moon, cargo flights, and eventually human flights. So this is again, this has been the goal since day one, and we're very big on the moon. In fact, when we founded Interorbital, we founded a nonprofit called Translunar Research, 501c3, and it's to commercially exploit and explore the moons of the solar system. We're heavily into the moon.
Oh, what is the nonprofit do? Could you, is it still running? And what
Yes.
does it focus?
Translunar Research, and founded that in 1996, actually. And we run a number of STEM programs through that. It's at translunar.org.
You could call it Translunar Development and Research, and then it would be TLDR.
There you go.
Oh, interesting. So it's what is the research focused on? I can't quite tell from it.
I'm sorry, I didn't hear you, Allison. It was breaking up.
What is the research focused on?
It's focused on living on the moon, actually finding a way to get to the moon economically and to set up human bases on different moons in the solar system. Our moon, we think in terms of moons of Mars, we think in terms of Europa and Triton, things of that nature. So we're looking out. And we want
Okay,
to
cool.
make it possible for anybody who wants to go there. Yeah. The next commercial zone is pretty much endless, right? Our rockets and the low price point that we will achieve with them is the way to go.
Do you collaborate at all with Open Lunar, or have you heard of Open Lunar?
I don't know them very much. I think I've attended a couple of their events, but it would be I'm always open to collaboration. I think it's great. And for something like that's the reason we founded a lunar nonprofit, because the challenge is so vast financially to do a moon base, right? And do the transportation system and things of that nature, that we needed a collaborative atmosphere, let's say, and a group to work towards that. So we're very interested in working with others towards that, and we're interested in providing the transportation system initially.
Do you want
And
to ask?
any findings that this nonprofit delivered?
In terms of it delivered our message to a number of the people that we educated through it, let's put it that way. We received some funding from the Foundation for the Carolinas to do STEM workshops in Compton, California. So we went straight into Compton, and we did rocket and satellite instruction courses there at tomorrow's Space Museum, I think it's called.
Hey, we only have 10 more minutes. I
Mhm.
want to take one or two of them to ask 2 more questions, and then Allison can ask her final question. First question is a programmatic question. Y'all have been working out there in Mojave for some time, and you have had a very interesting workforce composition that consists of some people out on the tails of the edge distribution. Both, you want to talk about that? You want to talk about that?
We do. We have folks who are hardcore scientists, right? And people who are trained in aerospace. We have people who are artists, people who will use space in many, many different ways. Okay. If
But you
fashion
also
designers,
have mined sort of some of these retirees and graybeards who
the
have
thing that's that unfortunately a lot of them are gone, but we were actively, particularly in the formative years of the company, we were actively recruiting people from, say, the what are now defunct aerospace companies that were the main builders of all the systems that were used in the space program. We had people from North American, people from Marquardt, people from Rocketdyne. These were retired engineers who had a lot to give and a lot of information to pass on. And this was guild knowledge. And just a quick aside, that's how we see our satellite kits. They're giving people the teaches them the black arts of how to make satellites because you can't get.
but on the
But
other hand,
these guys, yeah, yeah. These
on the
guys
other hand,
helped.
sorry, go ahead.
And they had been through it all. So they had developed the systems originally. A lot of these people were the originators of many of the systems that are in use today.
And on the other hand, you also have, or did have at any rate, you would have undergraduates and high school students out there turning wrenches and stuff. Isn't that
of
correct?
course. Yeah, and we're still working. We're building what's called a Mojave Spaceport Coalition, and we have, I think, about 11 different organizations involved in that. Many colleges in the area, Lawrence Livermore, a lot of diverse groups that are going towards this, and we're actually going to start doing podcasts from
Great.
the location with all the members of that group. So it's
So cool.
it's a desert. It's a desert economically, and in many ways, no opportunities for a lot of people there unless they're in the space business. So we're looking at a way to bring that neglected population that's in the desert into the.
Now, there's another thing. This is my penultimate question.
Mhm.
There's another thing, which is that some of these more non-traditional rocket companies, at any rate, they tend to reach into talent pools that are not traditionally associated with aerospace, like
That's right. And
welders and people like that, and riggers and welders and construction.
we see this as a giant construction project. So for us, and to follow along with our philosophy, we use nothing exotic. We use standard construction methods whenever possible, like people from shipbuilding or other industries have the skills to be able to build the systems that we're using. And we have an ocean launch component, we have a land launch component, we have completely mobile spaceports. That's the other difference in our company. We're not locked into a particular federal spaceport. We're working with a couple of new and upcoming spaceports, one near Yuma, and some our own launch location is our own private spaceport. Also, the licensing of a particular latitude and longitude on the ocean. And again,
Okay,
we're not fixed.
I'm going to skip my final question because I see we have a hand raised from Manuel.
Okay.
Manuel.
Yeah, hey guys, I hope you can see me. Yeah, I just want to ask, because I'm with Moondao, we are like the biggest Web3 community in the web that focus on space exploration as well. And we mapped our roadmap exactly as you did it here with these different research areas. And we're planning to do like research guilds, so working groups where we also incentivize our researchers who further develop the tech and maybe also make licensable IP out of this. So my question for you is, how do you plan to incentivize your researchers? And are you also planning to outsource some of the R&D tasks to maybe other institutions or R&D departments as well? So maybe more into the directions. Do you want to also become an Open Luna? But yeah, feel free to answer as you wish.
Yeah, and the way people are incentivized, in our program is that they get to work on something bigger than themselves. They get to work on what will be the railway to the moon, whatever you might want to call it. But this is there's nothing more exciting than rocket work. So, and how many people get to be close up and personal with a rocket engine test firing it. Not a lot. These are things that the work itself is the reward, and that's been the case for us as well. In terms of OpenLuna, I don't know the structure there, so I can't really answer that question. But we do contract work for other companies. Like we just finished something with Paragon Space Development Corporation, and that was great. And Avantis Federal and a number of other groups that we do work for, but we haven't contracted out work. Everything we do, we do in-house. And that's been the case so far, unless maybe some interesting concept comes up. If contact us, let us know if there's something you're interested in.
Awesome. Thank you very much for answering my question.
Okay, let's see. Allison, do you want to wrap it up?
I would love to ask my final question, which everyone who is presenting to a Foresight group gets, and which is if people are excited about your work and if people are excited about specifically supporting your guys' project, what are like a few open challenges and just kind of like bottlenecks that you're facing? How can people get involved and so forth? This is like a shameless plug moment.
Yeah. We have a set of test launches coming up. If people really want to be involved and help, they can buy advertising space on the rocket. They can invest in the company. They can do a number of things. And we have two methods that they can work through: the nonprofit, to just furthering the work on the Earth Moon transportation system that goes to the rocket work, or they can talk to us about investment in the company, since we have a small offering happening right now.
Okay,
And-
wonderful. And how can they find out more about you? Is it just going to your guys' website? Is that the best way
No,
to find out
They
more?
can call us. Their contact information on the website. They can call me directly. They can write to my email is ios@interorbital.com, and that goes directly to me. That's also on our website, which is interorbital.com. If you go there, you'll find the contact information. But and we're very happy to speak with people who want to be part of making this whole thing happen. We're not kidding around here. We've dedicated our lives to this. It's going to be spectacular, and it'll be so different when we reveal what we actually spent on our program compared to the multi-billions that other people have spent. I think it's going to be a real revelation.
All right. Thanks, everybody. Thanks, Allison. Thanks to all the attendees, and thanks to Rod and Randa for their holy work and their perseverance and their
Thank you
innovation.
guys for the opportunity, and lovely to meet you all today.